In this video, we were going to start our study of series. This is 8.2. I'm going to do the slides backwards. I'm going to do the second slide first. I would like to introduce the nth term test or the divergence test first. In the last video, we talked about sequences. So just let's do a little review. We said the limit as n goes to infinity of a sub n equals L, we would say that the sequence converges to some value. So for example, if I had, let's say 1, 1 over 2, 1 over 3, 1 over 4, dot, dot, dot. This is my a sub n is 1 over n, and we could say that the limit as n goes to infinity of a sub n equals 0. Either look at the terms, it's decreasing to 0, or we could just take the function and send it to infinity, we get 0. If I give you another sequence, let's say 1, 1/4, 1/9, 1/16, dot, 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 this also converges. I could say the limit as n goes to infinity of a sub n equals 0. So I look at my terms, they're getting smaller, it's getting closer to 0. This a sub n is 1 over n squared. So even if we drop this in and we did the limit, we would also get 0. So that's where we spent 8.1. If we were to add these up, if I was to add up these terms and did the series, so 1 plus 1/2 plus 1/3 plus 1/4, this diverges. And if I were to add this one up, 1 plus 1/4 plus 1/9 plus 1/16, this converges. So even though they both go to 0 for the sequence part of it, when I sum them up, one converges and one diverges. And that's the idea of the divergence test. So just because the sequence goes to 0 does not mean that the series will converge. It just means it may converge. So this will be the first test we use all of the time. So I'm just going to throw the tests out there real quick. So the first test will always be the nth term test, also called the divergence test. And then after that, we're going to get into geometric, p-series, integral test, direct comparison test, limit comparison test, alternating series test, we do ratio test, and we do the root test. So before we do any of these tests here in red, we have to get past the first test. So the first test is pretty simple. It's the divergence test, and it says that if the limit as n goes to infinity of a sub n does not equal 0, then it diverges. If it equals 0, it means we can move forward. It doesn't mean it converges. It just means it may or may not converge. Choose another test. So the divergence test we have to get past to be able to continue with the rest of the tests. So right now we're just testing divergence. So I'm going to look at the a sub n. So we do the limit as n goes to infinity of 2 to the nth power. If it doesn't equal 0, which it doesn't, it diverges. For here, we've got the limit as n goes to infinity. So I have n factorial over 2n factorial plus 1. We get 1/2, which is not equal to 0, so it diverges. So this one's interesting. Just because the sequence converges to 1/2, that's fine. When I add them up, it's still going to diverge because this doesn't equal 0. Limit as n goes to infinity, 1 over n. It does equal 0. So I can't at this moment state that this diverges. All I can say is from here we would have to choose another test. We can just move on because, and we'll do this in the next video, but this does diverge. The series diverges, but we don't know that until we do another test. The best we can say is the sequence goes to 0, so I can choose another test. When I do the other test, it's going to diverge. Okay, so just because it equals 0 doesn't mean it converges. It just means we can move on, pick another test. So limit as n goes to infinity. I take the highest exponent here. I'm just going to write a sub n right now. So I have -1 over 2, which again does not equal 0. So this is going to diverge. For number 8, limit as n goes to infinity. I have e to the 2n over n, exponential on top, polynomial on the bottom. This goes to infinity, which doesn't equal 0, so it diverges. And then the last one, we do the limit as n goes to infinity of a sub n. So I'm looking here. I'm looking at my exponents. Highest exponent is here. So this does equal 0. So that would tell me to choose another test. This, just for time here, I'm just going to write a sub n may or may not converge. We don't know that yet. We choose another test. So that's the divergence test. So although we formally did it here, when you run through all of these series, you're just going to do it quickly in your head. Just do a quick check of the divergence test. Okay, I can move on. And then we're going to choose another test. Okay, but for right now, we write it out. We say it diverges based off of the nth term test or the divergence test. Now I want to talk about partial sum and how we're going to use a partial sum to find the sum of the series. As we work through all of our tests, in the next video we're going to do geometric. So geometric would be something like this. We did geometric in pre-calculus. So something like that. If I was to list out the terms here, we would get a half plus a fourth plus an eighth plus a 16th plus dot, dot, dot. Not only does the sequence converge, but the series converges. Geometric allows us to find the sum of the series. There was a formula we used, so sum is equal to a sub 1 over 1 minus r. So we would say the first term, r is your common ratio, we're multiplying through by half, so we get 1. That means that if I add this up all the way to infinity, I get 1. Geometric is the only test that allows us to find the actual sum of the series. Every test we do, it gives us values. We get 1 often. It doesn't mean that it adds to 1. It just means that it converges. So geometric's the only test that we do that gives us the actual value of the sum of the series. So that's where partial sums comes into play. So first and foremost, a partial sum is, let's say I had this here. This implies we're going all the way to infinity. But if I said I wanted the fourth partial sum, it means I just want you to add up the first 4 terms. So this would be 1/2 plus 1/4 plus 1/8 plus 1/16. And it would be an estimate. But you'd be surprised, it's pretty accurate, but it's not exact. So if I added up the first 4 terms, it would give me an approximation of the sum of the series with some error involved, and we'll get to that later, but it's efficient, it works, okay? So a partial sum is adding up part of the series. So what I'm going to do is to create a sequence of partial sums. So what I want to do is create a sequence, so just a list of terms, but I want it to be a sequence of the sum of the first term, the sum of the second term, the sum of the first 3 terms, then the sum of the 4th term. So I want this to not be the terms of the sequence. I don't want this to be a sub 1, a sub 2, a sub 3, a sub 4. What I want this to be is the sum of the first term, the sum of the first 2 terms, the sum of the first 3, the sum of the first 4, the sum of the first 5, because if I can do that, maybe I can do the sum of the first infinite number of terms, which would tell me the sum of the series. So let's kind of work through it. Tough concept to grab, but we'll get through it. So first is saying, just find the fourth partial sum. So it's asking me to add up the first four terms. So let's do that. So we're going to get 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16. So the sum of the first four terms is 15 over 16. Now this is geometric. So I'm going to rewrite this as this. You're going to find that geometric is the easiest test that we do. So if I wanted to sum this up, I'd say, well, the first term is 1/2. R is 1/2. We just did this one, right? So a sub 1 over 1 minus r. So it's 1/2 over 1 minus a half. So this is going to give me 1. So that means the sum of this series is 1. Now look at the partial sum. I only added up 4 terms, and I got 15 over 16. That's pretty close to 1. So the more terms you add, which we're not going to do that right here, but if I added another, we're going to get a little bit closer. If I added another, we would get a little bit closer. So a partial sum, although it's not accurate, it's pretty darn close to the actual sum of the series. This one here would be 1 plus 1 plus 1 plus 1, which is 4. And then for this one, we would get negative 1/3 plus 1/4 minus 1/5 plus 1/6. And I get the sum of the first four terms is negative 7 over 60. Okay, so let's see if we can come up with this idea of a sequence of partial sums. So I'm going to add this on. It's not in your notes explicitly, but sequence of partial sums. So I want to start with this series. We just did it. So n equals 1 to infinity, 1 over 2 to the nth. So we know that this converges to 1. So it's if you plug this in, it's 1/2 plus 1/4 plus 1/8 plus 1 over 16 plus 1 over 32 plus dot dot dot. I know that it converges to 1. So let's see how we can use a sequence of partial sums. So what you're going to do is you're going to come up with a formula, an a sub n. We're trying to come up with a new a sub n that represents the sums, not the terms, but the sums. So how are we going to do that? Well, I would say start listing out the terms. So s sub 1 would be 1/2. S sub 2 is adding up the first two terms. So it's 1/2 plus 1/4, which is 3/4. S sub 3 would be 1/2 plus 1/4 plus 1/8, which is 7 over 8. Now you can see here it's getting closer to 1. This is a half, 0.5, 0.75, 0.875, I think, for this one. So it's getting closer and closer to 1, which we know that it's going to. So for each term that you add, it's going to get a little bit closer. So S sub 4 would be 1/2 plus 1/4 plus 1/8 plus 1 over 16 to get 15 over 16. S sub 5 would be 1/2, 1/4, 1/8, 1/16 plus 1 over 32. And we get 31 over 32. So what my goal is to create a sequence. So my first term is 1/2. My second term is 3/4. My third term is 7/8. So this is S sub 1, S sub 2, S sub 3, S sub 4 is 15 over 16, S sub 5 is 31 over 32. And I want to go all the way to infinity. So if I could do the limit as n goes to infinity of a sub n, which in this case is my s sub n, equals some value, that will tell me what the sum of the series is. So we need to come up with a formula. So as you look at this, you can start to see the pattern. When you do this yourself, when you work here and start doing this, you're going to start to see the pattern as you do this. So it's Definitely related to 1 over 2 to the nth power. 2 to the first, second, third, fourth, fifth. 2 to the first is 2, 2 squared is 4, 2 cubed is 8, 2 to the fourth is 16, 2 to the fifth, so it relates to the n here. Okay, but this is going to be 1 minus 1 over 2 to the nth power. So this is my new a sub n. So this a sub n represents the sum of each term. So a sub 1 is going to be 1/2, which is what this is. A sub 2 is going to be 3/4, which is what this is. So all I did was create a new sequence with the new a sub n. So if I want to find what this converges to, we just do the limit. As n goes to infinity, 1 minus 1 over 2 to the nth power. Plug in, this goes to 0, and I get 1.